Hello, today I'm going to present the graph algorithm design, the public transportation. And this picture showing a public transportation system. As you can see, the circle represents the station and the line represent the roads. So basically, the public transportation can be just represent a graph. The vertex of the graph will represent the transit station, which have information like the station name, the coordinates, even the ID of the station. And for the edges, they will represent the road between two stops. And it should be bidirectional because in real life the bus always goes to two direction, and be unweighted because in this problem the time travel between each have are approximately the same, and it also should have information like the normal edges from station from and station to. So the road from D to E and from the E to D should be considered as the different edge. Also, more importantly, it will have information of a road name, which indicate what bus or what line is run on this road. Like the blue line and the pink line, in this case, are considered differently. And for the graph itself, it can be represented by using a JSON list. And let me show how this method works when you want to add a road A to C to Z for bus 64. And you first just check if a C and A is like any of vertex is already on the graph or is in the adjacent list key. And if it is, and we just add a new edges independently to A and C. So we add edges A to C and from C to A and mark them as the roads for bus 64. Then we check if Z is not in the graph, we just initialize a new station Z and add it into an adjacent list. Then we create a road from C to Z and from Z to C to connect these two vertex or station. Next method is get transient path, which have a start and a destination. We need to find the path that's not necessary to be shortest path, but the path with the less number of transfer. And in this case, I'm thinking to use the DFS to find all possible paths from A to C, from the start to the destination. Then we just rank them as the number of transfer. So right here, I'm using the idea of dynamic programming, which may make my DFS run faster. And there's some point to be noticed is the address is bidirectional, which means the edges from D to E and from E to D are different. This is helpful for dynamic programming because if edges D and E have been memorized, and next time you go from E to D, you will call a wrong path if D to E and E to D are considered the same path. And I will show you how this algorithm will work. So this is a graph, and we just run. Our start is from A and destination is D. Let's do from A, and we have some variable to help, which I will include in this introduction. So let's go from A first, and then it's B. We do alphabetical order, and then it should be D, and we go C and go A. And in this case, A has already been recorded in the visitor, so this one will be a fail pass. Also, when we record pass, we just record the address instead of the station because only address have information of which path we are taken. Also, we update the number of transfer. For instance, once we move from A to B and to B to D, the number of transfer have been updated and been recorded maybe by integer. And then we move from D to E and from E to next one is F and G, and this pass is successful. Then this will be recorded into our dynamic programming or memorized, and this variable will have key as edge and value as another map. In this map, we record the path and the number of transfer in this memorized path. So next time we can just directly use it. And then we just do some backtracking back to F, back to E, and we try this pass by E, and we make goes to B because B is the visitor, so this one is a fail pass, and we go back to D because the blue and the pink edge is considered differently. So this time we go this direction. And then because E and F is already in our like dynamic programming, so we just use the exist path right there and add them both to the result with the number of transfer. Okay, and here's the result with the three shortest paths. It's not short, with the three paths with shortest number of transfer in Thai, and there are marked a different number on this picture. And next is rank transient path. We have a three-factor: number of transfer, total stop, and the cost. And we can we can mark them like with a different weight, because people may consider do not consider cost too much for the public transport, because they are kind of same price and not a lot. So I just weighted as a 0.1, and for transfer number of transfer is 0.5, total stop is 0.4, which all affect the time you take on the commuting. And here's here's the algorithm, and I will go specific with them in the example. Here's the example of finding the each score and total pass score for the pass 1. And here's the what is the total algorithm overall algorithm looks like for count the pass score. And the maximum transfer on this graph is 5 and maximum stop is 9. Then we just take pass 1 and do the transfer score, which is maximum transfer minus the number of transfer in this pass. So we get a 6. Oh, we get a 60. And then we do the stop score. We do a similar thing. We use the maximum stop score, number of stop minus how many stop is included in this pass, and divided by the number of maximum stop, and we get 33.3. For the cost score, the maximum cost would be the most expensive way in transfer times the maximum time of a transfer, so which will be 2 times 5. We use two to represent the cost for the line, and the 1 represent the cost for the bus. And then because on the pass 1 we didn't take the line, we only take the bus and do 2 transfer, so we have a 2 times 1 and 0 times 2. Then we still divide by the maximum number, and we get this score. After weighted by different weight factor, we got final score of 51.32. And here's the summary. We can find the pass 2 get highest score, and the pass 1, pass 3 are in Thai. This may make sense in the real life, because although the pass 2 have a cost like the money, kind of a little bit greater than the pass 1 and pass 3, but it have a minimum number of stops which save much time, and this one would be people like most preferred it to. So the last method is the get score test coffee path, which give a start and destination. You need to find the shortest path from start and destination, and the path through at least 1 coffee shop. So I'm thinking to divide this problem into 2. The first one is find shortest path from the start to each of a coffee store, and then do the same thing, find the shortest path from the destination to each of the coffee store, and then we just recombine them to find its minimum number of cost on the path of combined road. And here's here's the example of go from start by A to destination of G, and we need to quote at least 1 of the coffee store. So first we find the shortest path from A to each of C and H, CIH. We can just basically do this by running the Dijkstra's algorithm, because Dijkstra's algorithm can basically find shortest path between each of the 2 destination. Then we do the same thing to G, find shortest path from G to each of the coffee store, which is marked as the purple line on this graph. Then finally we just combine these two parts. So maybe for A to G and past coffee store C would be A to C to D to B to G. And finally you found cost. There's 2 costs are in Thai, and they are just the shortest path from A to G and past at least 1 coffee store. And that's all for my presentation. Thanks for listening.